Think about typical harmonic motion. Well, in order to think about typical harmonic motion, I guess we need to know what harmonic motion is. What does harmonic mean? I'm not going to write these down. You can write these down. We'll just discuss it. I'll pretend you're answering my question. Harmonic, yes indeed, means repeated, right? It's cyclical motion. So think about typical harmonic motion. Not simple harmonic motion, we'll define that in a second, but any harmonic motion. We talked about it in class a little bit, but harmonic motion includes things like a child on a swing, a pendulum, which is an example of a child on a swing, or a child on a swing is an example of a pendulum. A mass on a spring that oscillates up and down. But is there anywhere else? Like, why do we care about harmonic motion? Is there anywhere else we see harmonic motion? And the fact is that yes, while we idealize harmonic motion as masses on springs and simple pendulums, that harmonic motion happens every day. It happens in all kinds of, it's a very common physical phenomenon. For example, when you follow the point on a wheel that is spinning, that point goes through a cyclical process, right? It's also harmonic motion. It's two-dimensional harmonic motion, which if you break it up into the x and y component of its displacement or its velocity, then you will see that both the displacement and velocity and acceleration, acceleration... the x and y components of acceleration, velocity, and displacement all undergo harmonic motion. They all repeat themselves. They go back and forth and back and forth and back and forth. They all repeat themselves. So that's just a wheel. But what else? Atoms in a solid, right? Atoms in a solid are modeled as masses on springs. It's harmonic motion. And this is how we understand the chemistry and the physics of solid materials. Object floating in the water, right? When an object floating in the water undergoes harmonic motion, or waves in a water. Waves, yes, waves themselves are examples of harmonic motion. And where we want to go with this description is we want to get to where we understand waves and wave motion, because that is an essential part of quantum mechanics. But in order to understand waves, we've got to understand harmonic motion. So waves are more complicated harmonic motion. They have additional components involved as well as harmonic motion. But what I was sort of saying to begin with is if you have an object like a buoy floating in the water and waves come by, what happens? The buoy goes up and down and up and down and up and down. It undergoes harmonic motion, right? So you can see that is sort of a component of the wave motion. A marble in a bowl. If you have a marble in a bowl and you lift that marble up one wall and you let it roll down, it's going to roll up the other side and back and forth and back and forth. Now you might say, well, is it harmonic motion? Because it's only going to go up and down a couple times, it's going to stop. Well, that is harmonic motion. That's not simple harmonic motion. That's a damped harmonic motion. So there's different kinds of harmonic motion. We're going to start by talking about the simplest, which is simple harmonic motion. And then in this class, we're actually not really going to, I don't think we're going to really address a damped harmonic motion. That's just adding friction. And so that just means that the motion gets smaller and smaller and smaller as we go. And then driven harmonic motion. That's where you actually drive the thing to keep going. So a child on a swing is both driven and damped harmonic motion. If you let the child go without pushing them, they will come to a stop, but you keep on pushing them. You drive that harmonic motion. So there's driven, damped, and simple harmonic motion. We understand harmonic means that it's repeated, but what are the characteristics? That's the word I was looking for. The characteristics of harmonic motion. Characteristics of harmonic motion is that there is an equilibrium point, right? And that equilibrium point is what? Equilibrium we have defined in many different aspects or many different times in many different parts of physics. Equilibrium means that the net force is equal to zero. It also, when you allow for rotation, also means the net torque is equal to zero. But it means the net force is equal to zero. That is where the body the mass that we're discussing that's undergoing harmonic motion would stay if we put it there, right? It's not going to go anywhere. So in harmonic motion, what we do is we disturb something from equilibrium. And this, again, from what you know about waves, you should understand that this sounds a lot like waves also. We disturb the body from equilibrium, and what happens? The body wants to go back to equilibrium, right? So the body wants to go back to equilibrium. So, for example, the typical example is the mass on the spring, right? If I hang that from ceiling, it's going to tend to sit at some equilibrium position. We just call that x equals 0, equilibrium. And what happens if we disturb it from equilibrium? If we lift it up, right? If we push it up away from equilibrium so that it is here, right? What's going to happen is the mass will tend to fall back down. It will want to fall back down towards equilibrium. But because if we drop it from rest, if we lift that mass up attached to the spring and we drop it from rest, right, once it reaches equilibrium, what does it do? It's got a velocity, so it's going to keep going. So that mass goes all the way down to here until finally, right, once it passes equilibrium, that spring is trying to stop it from going any further, and it's going to finally come to a stop. And now the spring is stretched beyond its equilibrium position, and it's going to pull it back up towards the equilibrium position. So when you disturb a body from equilibrium, it oscillates around the equilibrium position. I'm just going to abbreviate equilibrium EQ. It oscillates around the equilibrium position. So that's the qualities of those are the characteristics of harmonic motion. That there's equilibrium, and the body just continually. The reason why it undergoes harmonic motion is because it continually tries to get back to equilibrium. Now that doesn't hold for circular motion, because when you look at a wheel, it's not like the rim of the wheel is trying to get back to the center of the wheel. But there's an equivalence there that we can draw with a wheel. But when we're talking about pendulums and springs and a buoy in a water, etc., those are always objects that have an equilibrium position, and they're just going to oscillate about that equilibrium position. I guess the one thing I didn't say that should be pretty obvious is that when you're away from equilibrium, the net force is no longer zero, and the net force always pulls you back to equilibrium. So F net always points towards equilibrium. That is the characteristic of harmonic motion. So I drew different arrows, right? The two arrows on the right are just indicating there's a force pulling it back towards equilibrium. The arrow on the left was indicating that I physically was pulling that block up away from equilibrium. So anyway, those aren't really meaningful. So now let's talk about simple harmonic motion, right? Simple harmonic motion. Simple refers to something in particular. It's not just a qualitative word. It's actually quantitative. Simple harmonic motion. Abbreviated SHM. I will use SHM. I will not write out simple harmonic motion anymore. Simple means what? Who knows what simple means? You learned this in high school if you took physics in high school. Simple means that restoring force, I didn't call this, but it's called the restoring force because it always points back to equilibrium. It's called the restoring force. It doesn't matter what the restoring force may be. The spring force. The restoring force may be buoyancy in the water. Whatever the restoring force is, it points back towards equilibrium at all times. So what that means is that if the body moves away from equilibrium in a displacement in that direction, what direction is the restoring force? The restoring force is in that direction. Or if the body moves away from equilibrium in that direction, the displacement in that direction, what's the direction of the restoring force? The restoring force is in that direction. So the restoring force is always in the opposite direction of the displacement, right? The restoring force is always in the opposite direction of the displacement. But what's the restoring force equal to? Well, don't think that there's an answer to that because the restoring force is equal to, it's depending on the physical situation we're in. But with simple harmonic motion, it is a special case where the restoring force is proportional to the displacement. The restoring force is proportional to the displacement from equilibrium. So I'm not going to write those words, but that's what this says. The restoring force is proportional to displacement from equilibrium. And of course, the restoring force is in the opposite direction of the displacement from equilibrium. So we might write something like the restoring force is, if it's proportional to, then it must equal minus k delta x. What do I mean by that? Right? The minus sign indicates harmonic motion. The restoring force is in the opposite direction of displacement. The fact that that the restoring force is proportional to displacement, right? This is a proportionality constant. I won't write those words, right? So the first arrow was saying it's harmonic motion. The restoring force always points in the opposite direction of displacement. The second arrow indicates a proportionality constant, k, just some arbitrary proportionality constant. And then this is, F is proportional to delta x. In some other, right, something else, you could have F is equal to minus k delta x squared. In that case, it's not simple anymore, right? It's something else. So there's still a minus sign, there's still a proportionality constant, but it's proportional to x squared. So this is not simple. Okay, simple harmonic motion. So you might say, well, that's just the spring force. Well, but this is the generalized simple harmonic motion. And it is indeed what you get for a mass on a spring. Hooke's law, just as an aside, we know that Hooke's law, we did Hooke's law in Physics 115, 116, is that the spring force, which is the restoring force when you've got a mass on a spring, the spring force is equal to minus k delta x, where delta x is the displacement from equilibrium of the mass on the spring. So that is indeed Hooke's law. But in general, you can always write simple harmonic motion restoring force as some kind of proportionality constant to displacement with the minus sign. So this would hold also for a pendulum. It's just that the proportionality constant is something different than the spring constant. Okay, hopefully that made a little bit of sense. So speaking of buoys in water, what do you call a fish with no eyes?